Principia Mathematica, Part 1, Section B, Video 2. In this video, I'll be continuing what was started in the previous video and taking a look at the remaining sections of Section B of Part 1, Sections 12, 13 and 14. There's a lot of detail to go through for these sections, particularly Sections 12 and 14. Section 13 will be relatively short though. Please be aware that I cannot guarantee the correctness of the derivations of the functional hierarchy that I give relating to the axiom of reducibility in Section 12. As you may appreciate, it's not easy to find information regarding some of the aspects of Principia Mathematica, and there are not exactly many people around who I can ask for help when I get stuck. Therefore, the derivation is what I've been able to figure out from the information that is there in Principia Mathematica, and is based on my own interpretation of that information. This has not at all been an easy task, and there are still some aspects that I feel a bit unsure about. If you do happen to know a thing or two about Principia Mathematica, and you see that I've misinterpreted something, then please let me know, because I'd be very keen to know if there's anything that is wrong. So let's get started. Section 12. The hierarchy of types and the axiom of reducibility. This chapter is devoted almost in its entirety to the explanation of the functional hierarchy and the axiom of reducibility. The axiom of reducibility, or rather axioms of reducibility, are introduced at the end of Section 12. Of course, I could just present the primitive propositions 12.1 and 12.11 and then move on to the next section. However, the axiom of reducibility can't be properly understood without a certain amount of explanation. I've also chosen to devote a large part of this video to an explanation of the functional hierarchy and the axiom of reducibility because of the personal interest that I have in these two concepts. So before I introduce the axiom of reducibility, I'll be going into some considerable detail in relation to the derivation of the functional hierarchy. If you don't want to sit through this derivation, then I'll leave a timestamp in the description for you and you can go straight to the statements of the axiom. Though, if you're not too familiar with the functional hierarchy, then don't be too surprised if the axiom doesn't really seem to make any sense. I'm going to start off this video giving a bit more of an idea about what motivates the theory of types. I mentioned in the first video that the theory of types was Whitehead and Russell's solution to certain paradoxes, which had started to be noticed in logic and mathematics around the end of the 19th and start of the 20th centuries. These paradoxes are what Russell called paradoxes of a vicious circle kind. On pages 63 and 64 of the introduction, Whitehead and Russell give 7 examples of paradoxes of this kind. Amongst these examples we find Brawley-Fortey's paradox of the greatest ordinal number, the class of all those classes which are not members of themselves, also known as Russell's paradox, and the paradox of the least indefinable ordinal, and so on. And we read on page 64, in all of the above contradictions there is a common characteristic, which we may describe as self-reference or reflexiveness. Therefore, Whitehead and Russell's answer to this is to eliminate this reflexiveness. We'll see how the construction of the functional hierarchy forbids this reflexiveness to the extent that paradoxes of the vicious circle type do not and cannot appear. But I just want to clarify what's meant by type. We've already come across the definition of being of the same type in Section 9, that's definition 9.131. A type is defined on page 168 to be the range of significance of some propositional function. This is effectively what the primitive proposition 10.122 says. Therefore, we can't have types which exist independently of propositional functions. We also saw in definition 9.131 that individuals form the lowest level type. And on page 169 we see, we may explain an individual as something which exists on its own account. And we also see on page 54, such objects, individuals, will be genuine constituents of propositions or functions, and will be genuine constituents in the sense that they do not disappear on analysis, as for example classes do. Therefore, since individuals form a type, the totality of individuals must be the range of significance of some propositional function. Recall that any propositional function which is significant on one value of a certain type is significant on all values of that type. Any one of the variables of a propositional function, therefore, must range over the whole of a type and not just a part of it. And also, a variable cannot range over more than one type. Individuals, therefore, form the lowest level of the functional hierarchy. The functional hierarchy will take some time to explain. In Principia Mathematica this is made somewhat more confusing by the fact that there are effectively 2 differing derivations, one in the introduction and one in section 12. I will be, in a way, going through both of these derivations, though they will kind of blend into one another to a certain degree. The derivation in section 12 is a more refined derivation, but because of this some of the details about how things work in the background are more obscured. Therefore, I'll start with the derivation of the functional hierarchy that we see in the introduction, and then I'll gradually move to the derivation given in section 12. We can have propositional functions of any finite number of variables, each variable ranging over the totality of individuals, and this can be summarised in the diagram. So far so good. Now, individuals form a legitimate totality, and so we can start to introduce apparent variables by generalising some of the variables which appear in the propositional functions. I'll just use the always type of apparent variable here to illustrate, but of course we can also generalise using the sometimes apparent variable. This process of generalisation can be summarised as in the diagram on the screen. By generalising all of the real variables of a propositional function, we obtain propositions. Indeed, all of the functions in this diagram, since they have variables which range over the totality of individuals and over no other totality, and possibly apparent variables of individuals, are called first-order functions. A first-order function with no apparent variables is called a first-order matrix. A first-order function whose every real variable has been generalised is called a first-order proposition. Thus we see that first-order matrices are the source of all first-order propositions. Notice that when we start with, say, the function phi xy of two variables, both ranging over individuals, then when one of these variables is generalised, that is, made into an apparent variable, then we end up with something like for all x phi xy, which is, of course, a function of a single variable which ranges over the totality of individuals. Similarly, we can take a function of three variables, phi xyz, and generalise two of the variables, which is again a function of a single variable which ranges over individuals. Therefore we see that functions of a single variable ranging over the totality of individuals can have different forms. As it stands, we can't say whether all functions of a single variable which ranges over individuals are first-order functions. However, suppose we form the function f phi blank x, which has two variables. One variable x ranges over the totality of individuals, and phi blank is a variable which ranges over the totality, in inverted commas, of functions, not necessarily first-order functions, which have a single variable ranging over the totality of individuals, and we will assume that this is a legitimate totality. In that case, by generalising the variable phi blank in f phi blank x, we obtain the function for all phi blank f phi blank x. This is of course a function of a single variable x, which ranges over the totality of individuals. It's not a first-order function because first-order functions are those functions which have apparent variables of individuals. This function has an apparent variable of a certain kind of function, and of course functions are not individuals by definition. Therefore this function, for all phi blank f phi blank x, must be in the range of the variable phi blank, since the range of phi blank was all functions of a single variable, ranging over the totality of individuals. But this can't happen. As we know, a function can't have as a possible argument any argument which refers to the function itself. We also see on page 168 that, in order to avoid the vicious circle paradox, any expression containing an apparent variable must not be in the range of that variable. Thus it seems that there is no legitimate totality of all functions of a single variable which ranges over the totality of individuals. Can we just restrict the range of phi blank to the first-order functions then? Well yes, but we still have to have some restrictions. For example, the values of the first-order matrix phi x are elementary propositions, and the values of the first-order function for all y psi xy are first-order propositions. To avoid the vicious circle paradox, elementary propositions and first-order propositions must form different types. Therefore, we may choose our variable phi blank to range over first-order matrices, or we might have it range over first-order functions of the form for all y psi xy. We may have the variable phi blank range over any of the various other possible forms, but whichever we choose, we must limit its range to functions of that form if we are to avoid the vicious circle paradox. Indeed, we could even have phi blank ranging over functions of the form psi blank f psi blank x if we really wanted, where psi blank is a variable ranging over some type of first-order functions of one variable. We will see that through the construction of the functional hierarchy, whichever range we choose for psi blank, for all psi blank f psi blank x will not be a function in that range. Therefore, we see that some of the nodes in the diagram shown earlier correspond to different types, that is, the range of significance of some propositional function, since we can have a function fx where x is a variable which ranges over functions of the form phi x, or functions of the form for all y phi xy, and so on. Indeed, we will treat each of the nodes as corresponding to a different type. And of course it may be asked, how do we know that each of the nodes corresponds to a different type? The answer to this is because we decide that that will be so. And this seems to be the right way round. After all, the values of a function, and hence its range of significance, are presupposed by the function. That is, the values come first and the function second. Therefore, we cannot discover what are the ranges of significance of functions by looking at the various ranges of significance of functions. We have to decide what we want to have as the possible ranges of significance, or types, first, and then there will be a function corresponding to it, since a type is defined on page 168 to be the range of significance of some function. If the ranges of significance are well chosen, then we will successfully avoid the vicious circle paradox, and if the ranges of significance are not well chosen, then we won't. We have every reason to be very strict in the ways in which we divide things up though. Going forward, the symbol phi exclamation mark blank will be used to indicate a variable which ranges over a suitable type of first order function, but not first order propositions. For the time being, we'll call the values of phi exclamation mark blank predicative functions of individuals. We may simply refer to phi exclamation mark blank itself as a predicative function, in a similar way to which x is often referred to as an individual, even though it's arguably a variable ranging over the totality of individuals. Different variables of course may range over different types of first order function, and so what is meant by predicative function is relative to the variable in question. For example, if we choose the variable phi exclamation mark blank to range over first order matrices, then in this case first order matrices will be the predicative functions of this variable. If we choose phi exclamation mark blank to range over first order propositions of the type for all x and y, phi x, y, z, then functions of this type will be predicative functions for this variable. Of course, similar notation is used for variables which range over a suitable totality of first order functions of two variables, for example, phi exclamation mark blank blank, and so on. Thus, with our new variables, we can create a new type of function, second order functions. Second order functions are functions which have variables which range over the totality of individuals and or any suitable totality of first order functions and no other totalities. Moreover, a second order function must have at least one variable, whether real or apparent, which ranges over a suitable totality of first order functions. Analogously with first order functions, we have second order matrices, and these are second order functions with no apparent variables. Some examples are shown on the screen. Second order functions, these may be matrices but may have some apparent variables but have at least one real variable. And note that we can have apparent variables which range over first order functions provided that they range over one of the legitimate totalities of first order functions that we've decided upon. And finally we have second order propositions. These are second order functions whose every real variable has been generalized. Analogously with the first order case, we see that second order matrices are the source of all second order propositions. At this stage there's a huge range of possible types of functions. A few of these functions are shown on the screen now. In the examples given in Principia Mathematica of second order functions, there appears to be an error which is highlighted on the screen now. There exists x, phi x, psi x should be there exists x, phi exclamation mark x, psi exclamation mark x. Note that in the case where we have two variables ranging over a type of first order function, we do not require them to be of the same type. Once again though, we can divide second order functions up into types and form variables which range over the various types of second order function, but again not propositions, often written f exclamation mark with suitable variables indicated in the brackets. The values of the variable f exclamation mark may be called predicative functions of first order functions and individuals. Again, we may just refer to f exclamation mark itself as a predicative function, and it will be clear from the context the specific nature of the predicative function which is meant. These variables can then be used as variables in third order functions, and so on. And thus in a similar way, we can form functions of any finite order and with any finite number of variables. Earlier in the video, we were not in a position to determine whether all functions of a single variable ranging over the totality of individuals are first-order functions. We can see now that this need not be the case, and we can now see why. Suppose we have the second-order function f phi exclamation mark blank x, where x ranges over the totality of individuals and phi exclamation mark blank ranges over some suitable type of first-order function. Then we may generalize this function to give, for all phi, f phi exclamation mark blank x, and note that phi is used in the apparent variable rather than the strictly more correct phi exclamation mark blank as indicated on page 172, and it can be seen that this is a second-order function of a single variable which ranges over the totality of individuals. Thus we see that not only do we have different types of first-order functions of one variable ranging over individuals, but we also have different order functions of one variable ranging over individuals. This is the essence of the ramified theory of types in contrast with the simple theory of types. Therefore, the type of a real variable, or types of the real variables, does not determine the order of the function, since we can have, for example, a function which has a single variable ranging over some type of first-order function, but the function whose variable this is may be a third-order function, depending on the specific case. We could similarly form functions of any order which have a single real variable ranging over the totality of individuals. In the article Infinite Regress and Foundations of Mathematics by Imre Lakatos, in the book Mathematics, Science and Epistemology, Philosophical Papers Volume 2, Lakatos describes the ramified type theory of Whitehead and Russell as one of the most complicated conceptual labyrinths a human mind ever invented. Some important features of the functional hierarchy are, firstly, an nth-order matrix has no apparent variables and contains at least one real variable which ranges over a suitable type of n-1th order functions. Matrices are always of order 1 greater than the greatest order amongst the variables. Secondly, any nth-order function, whether matrix or not, has at least one variable, whether real or apparent, which ranges over some type of n-1th order function. However, depending on the specific case, an nth-order function may not be of order 1 greater than the greatest order to be found amongst the real variables. So it appears that our functional hierarchy is complete, and it is in a sense, but there are certain problems with it, namely, it's very complicated. This is really only an issue of convenience. Of course, sometimes things are just complicated and we have to deal with that. However, a more pertinent issue is that, say we choose a variable phi exclamation mark blank to range over a certain type of first-order function of one variable, then obviously not all functions of that one variable are accounted for in that range. How do we know that the range of functions that we've chosen is wide enough? And this is where the axiom of reducibility comes in. Unfortunately for us, the axiom of reducibility will, apparently, solve both of these issues. Since we're only interested in truth functions, then we really only need to take into consideration the extension of a propositional function, that is, roughly speaking, the arguments for which the function is true. The axiom of reducibility is proposition 12.1 as shown. Or, for the case of two variables, not necessarily ranging over the same type, proposition 12.11, also called the axiom of relations. And indeed, there would be a separate axiom of reducibility for every finite number of variables. What 12.1 says then is that every function of one variable is formally equivalent to a predicative function of that variable. Thus, to take an example, suppose we've chosen the variable phi exclamation mark x to range over first-order functions of the form for all x phi xy. Therefore, functions of the form for all x phi xy are our predicative functions. Then the axiom of reducibility, 12.1, says that for any non-predicative function, fx, of a single variable which ranges over the totality of individuals, which can be of any type or any order, there exists a predicative function of the form for all x phi xy, which is formally equivalent, but not equal to, the function fx. In other words, the truth values of fx and for all x phi xy are identical for each and every value of x. Similarly, for any function, there will always be a suitable predicative function of the same variable to which it will be formally equivalent. Therefore, we see then that since we're only interested in truth functions, by introducing this axiom, we can ensure that the range of phi exclamation mark blank doesn't miss out any possibilities. It's not, after all, the specific nature of the propositional function that is important to us. Rather, it's the extension of the propositional function. And on page 77 we see, when two functions are formally equivalent, we may say that they have the same extension. There's a very obvious simplification that can be made then at this stage. Suppose we have the second order function f phi exclamation mark blank psi exclamation mark blank, where each of the variables ranges over some type of first order function of one variable. The types that these variables range over need not be the same type, but in light of the axiom of reducibility, we can assume that they do range over the same type. We could of course choose this type arbitrarily if we wanted to. However, there doesn't seem to be any reason to make things more complicated than they already are. We may as well assume that the type that each of the variables ranges over is first order matrices of a single variable, since arguably this is the simplest option. Again, we're free to choose as we wish. There is no absolute notion of predicative function, and there's nothing special about matrices other than they seem to be the simplest option. So henceforth, the variable phi exclamation mark blank, which ranges over a type of function of a single variable, which ranges over the totality of individuals, will always be assumed to range over first order matrices of a single variable. Thus, first order matrices of a single variable will be the predicative functions. No other type of function of a single variable ranging over individuals will be called predicative from now on. There's nothing inherently wrong with non-predicative functions. They are simply the types of functions that have not been specifically chosen as being predicative. Of course, non-predicative functions still form types, that is, they are still values in some propositional functions. It's just that we don't need to consider these functions anymore. Note that non-predicative does not mean the same as impredicative. An impredicative function is a function which appears amongst its own values, or, in other words, a function which is defined in terms of itself. Similarly, the variable phi exclamation mark blank blank will always be chosen to range over first order matrices of two variables, and no other type of function of two variables, both of which range over individuals. As a final example, the variable f exclamation mark phi exclamation mark blank will always be chosen to range over second order matrices of one variable and no other type of function. Continuing in this way then, we always choose our predicative functions as being suitable matrices. Thus we have arrived at a point where matrices and predicative functions are entirely synonymous. Previously, they were not synonymous since, depending on our inclinations, we could have chosen a variable to range over a type of function other than matrices. Indeed, we see on page 54, Whitehead and Russell say, this use of the word predicate is only proposed for the purposes of the present discussion. And on page 172 we see, a function is said to be predicative when it is a matrix. Therefore we see that predicative has a broader meaning in the arguments involved in the introduction relating to the functional hierarchy. But the meaning of predicative has been narrowed in section 12 to be synonymous with matrix. Note that the notions of predicative function and matrix are taken as primitive ideas. See page 172. Reading through the derivation of the functional hierarchy given in section 12, we see that it's a more refined derivation than the one found in the introduction. However, I believe that the more detailed derivation in the introduction gives some important clues which help one to better understand why some things are the way that they are. For example, it would possibly seem strange and a possible redundancy in terminology for predicative function and matrix to be synonymous. However, the introduction makes it clear that this need not be the case and happens to be the case because of a particular, yet theoretically arbitrary choice that we have made. There are some further simplifications that the axiom of reducibility brings. For example, since for any function we can always find a predicative function or matrix which is formally equivalent to it, then we really only ever need to consider functions that are of an order 1 greater than the greatest order to be found amongst the real variables of the function, since this is a property of matrices. Moreover, since we have no absolute notion of order in our functional hierarchy, then we only need to consider relative types, and so, in the case that we have a function of one variable, not only can we assume the function to be formally equivalent to a matrix, we can redefine the type over which the variable ranges to be our totality of individuals, and thus we can effectively treat the function as a first order function. Systematic ambiguity will step in and shift the meanings of the relevant symbols to match the types involved. Of course, it may still be necessary to consider particular functions of unknown order relative to its variables, and we may write, for example, phi x to represent such a function of one variable. But this represents a particular function and not a variable function. The axiom of reducibility is not without its own problems, though. In fact, the axiom of reducibility was a fly in the ointment for Whitehead and Russell. Much controversy surrounded the question of whether the axiom of reducibility was indeed a purely logical principle, and whether it was self-evident or whether it could in fact be proved. Even Whitehead and Russell seem to have been unsure about it. After all, they include a section in the introduction, page 62, titled Reasons for Accepting the Axiom of Reducibility, where the first line reads, that the axiom of reducibility is self-evident is a proposition which can hardly be maintained. But in fact, self-evidence is never more than a part of the reason for accepting an axiom, and is never indispensable. So it seems that Whitehead and Russell had already decided to hedge their bets a bit regarding the axiom of reducibility, even in the first edition of Principia Mathematica. And I certainly don't want to get into a full-blown critique of the axiom of reducibility, but I personally find the axiom of reducibility fascinating because of the controversy that it caused. Frank Ramsey has much to say concerning the axiom of reducibility in his 1925 article, The Foundations of Mathematics, which can be found in the book The Foundations of Mathematics and Other Logical Essays. In this article, for example, we read, so as the process of deduction is such that from tautologies only tautologies follow, were it not for one blemish, the whole structure of Principia Mathematica would consist of tautologies. The blemish is, of course, the axiom of reducibility, which is, as will be shown below, chapter 5 of the present article, a genuine proposition, whose truth or falsity is a matter of brute fact, not of logic. It is therefore not a tautology in any sense, and its introduction into mathematics is inexcusable. So much for the functional hierarchy and the axiom of reducibility. But Whitehead and Russell make several allusions to the propositional hierarchy in Principia Mathematica, and there are instances where propositions appear with apparent variables ranging over a type of propositions rather than a type of function. Apparent variables ranging over a type of proposition are seldom used by Whitehead and Russell. One instance is in section 14, the demonstration of proposition 14.3. However, Whitehead and Russell say regarding this proposition, in this proposition, 14.3, the use of propositions as apparent variables involves an apparatus not required elsewhere, and we have therefore not used this proposition in subsequent proofs. And following the demonstration of this proposition, we see the following propositions, following 14.3, are immediate applications of the above, 14.3. They are, however, independently proved because 14.3 introduces propositions, P and Q namely, as apparent variables, which we have not done elsewhere, and cannot do legitimately without the explicit introduction of the hierarchy of propositions with a reducibility axiom such as 12.1. Propositions as apparent variables also appear elsewhere, especially when giving examples to illustrate, say, systematic ambiguity. Therefore, we see on page 44 of the introduction and page 134 of section 9, propositions appearing as apparent variables. However, these examples are merely for illustrative purposes and are not part of the deductions of Principia Mathematica. Proposition 14.3, as we have seen, is an isolated case of which no further use is made. To allow propositions as apparent variables would require the derivation of the propositional hierarchy. This is not done in Principia Mathematica, since it's never needed in Principia Mathematica, but that's not to say that it isn't needed or used elsewhere, but simply that it's not needed or used in Principia Mathematica. On pages 57 and 58 of the introduction, Whitehead and Russell indicate how the propositional hierarchy may be derived from the functional hierarchy. There's less than a page explaining this, and I don't find it to be very clear. I'm not totally convinced by it though. I certainly wouldn't go so far as to say that I think that it's wrong. We see, however, on page 58, the propositional hierarchy can therefore be derived from the functional hierarchy, and we may define a proposition of the nth order as one which involves an apparent variable of the n-1th order in the functional hierarchy. We also see the propositional hierarchy is never required in practice and is only relevant for the solution of paradoxes. Hence, it is unnecessary to go into further detail as to the types of propositions. Therefore, I won't go into any more detail regarding the propositional hierarchy. I have not managed to go through all of the details of it, though I have spent some time trying to do so, and quite unsuccessfully. A natural question to ask is, why did Whitehead and Russell decide to use the functional hierarchy instead of the propositional hierarchy? And I can't give a definitive answer to this, but there are some passages in Principia Mathematica which may go some way to indicating what the reasons may have been. For example, on page 169 we see, we may explain an individual as something which exists on its own account. It is then obviously not a proposition, since propositions, as explained in chapter 2 of the introduction, page 46, are incomplete symbols, having no meaning except in use. And to repeat a passage which I've already quoted earlier in the video, on page 54 it reads, such objects, individuals, will be genuine constituents of propositions or functions, and will be genuine constituents in the sense that they do not disappear on analysis, as for example classes do. And therefore it seems that individuals, which are the lowest level in the functional hierarchy, are not incomplete symbols. They exist in their own right. Individuals are constituents of propositions, and therefore appear to be more fundamental than propositions. Individuals cannot be further analysed. It also appears that by using propositional functions, we're able to divide propositions up in certain ways, such as all those propositions which have a certain constancy of form. That propositions are incomplete symbols obviously does not mean that they cannot form their own hierarchy. As we've seen, they do, and indeed we see in sections 20 and 21 that classes and relations, which are also incomplete symbols, form their own hierarchies, and more will be said about these when those sections are covered. The propositional hierarchy does seem to have the advantage of being slightly easier to use and understand when it comes to illustrating certain aspects such as paradoxes and systematic ambiguity. Thus, although systematic ambiguity is explained in terms of, effectively, the propositional hierarchy, and since the propositional hierarchy can be derived from the functional hierarchy, then the issue of systematic ambiguity is, or was, also a problem concerning the functional hierarchy, and we haven't just wasted our time resolving that issue in sections 9 and 10. To round things off then, let's have a look at how the functional hierarchy resolves the vicious circle paradoxes that Whitehead and Russell are hoping to eliminate. In the hierarchy, it can be seen that a function of a certain order can only take arguments from those types in the hierarchy which are lower in the hierarchy, that is, which have a lower order. In the construction of the hierarchy, the lower orders are naturally presupposed by the higher orders, and so the values of a function are presupposed by the function, and therefore no function could ever appear amongst its own values. An expression such as phi of phi blank cannot occur in the way that the functional hierarchy is constructed. Such an expression represents nothing more than a meaningless string of symbols. Thus, the vicious circle paradoxes can never appear. Moving on to section 13, we're introduced to the definition of identity. This is quite a short section, but there are still a few points that are worth making about identity and some of the propositions in this section. Notice that in the definition of identity, the apparent variable, of course, ranges over predicative functions. Indeed, on page 176 we see, this definition states that x and y are to be called identical when every predicative function satisfied by x is also satisfied by y. We can't extend the range of the apparent variable to range over all functions for the reasons that we saw in section 12, that there is no legitimate totality of all functions of x. However, because of the axiom of reducibility, we know that every non-predicative function is formally equivalent to a predicative function, and so the definition of identity, definition 13.01, along with the axiom of reducibility is as powerful as it would be if it could be extended to cover all functions of x. Definition 13.01 is converted to an equivalence, and hence an actual proposition, in proposition 13.1. Proposition 13.101 is almost an extension of definition 13.01 in the sense that 13.101 states that if x and y are identical, then if a function is satisfied by x, the same function is also satisfied by y. In this proposition there is no apparent variable. The psi is not a variable, though of course it can be replaced with any particular function. And I find the comments following the demonstration of this proposition to be quite interesting. That in the absence of the axiom of reducibility, we could only obtain strict identity by introducing the notion as a primitive idea. Otherwise, we would only be able to obtain identity with respect to a particular type of function on which x and y agreed. Thus, it would be possible for x and y to be identical with respect to some types, but not with respect to others. Interestingly, Frank Ramsey disagrees with this in his article The Foundations of Mathematics, where he argues that rejecting the axiom of reducibility would not lead to a weakening of this definition of identity. Proposition 13.12 strengthens the material implication and the consequence of 13.101 to an equivalence, and Proposition 13.11 strengthens the formal implication of 13.1 to a formal equivalence. And Propositions 13.15, 16 and 17 show that identity is an equivalence relation. Of course, it may seem redundant to check that identity is a reflexive, symmetric and transitive relation. However, suppose we settle on a particular definition for identity. We can then take this definition of identity as the definition, and we will stick to this definition and accept whatever consequences follow from it, even if that means that certain unexpected or potentially undesirable consequences follow, such as lack of transitivity. On the other hand, in reality, we already know what kind of relation we would like identity to be and what kinds of properties, at least on a basic level, we would like identity to satisfy. We know, for example, that we would like our notion of identity to be a transitive relation. Then, should this property fail according to our definition, then we would consider our definition defective, and we would be prepared to replace it with a more suitable definition. And of course, this latter option would be better. But there's no guarantee that just because we define identity in a certain way, which appears to be reasonable at first glance, that it will automatically lead to all of the desirable properties that we have in mind. Suppose our definition is defective in that it doesn't satisfy the transitive property that we would like identity to have. If we check for transitivity and it fails, then we know that our definition is defective. On the other hand, failure to check for transitivity means that we may not realise for some considerable time that we have a problem. The defect may show up elsewhere and much later, but it could have been caught earlier. Therefore, there is some value to checking these seemingly trivial properties in the first instance. Many of the propositions in this section are propositions which will be used in later sections, and particularly in section 14. The propositions themselves in many cases have no real intrinsic interest, but nevertheless, their importance shouldn't be overlooked. On page 23 of the introduction we read, "We shall find that no new definition of the sign of equality is required in mathematics. All mathematical equations in which the sign of equality is used in the ordinary way express some identity, and thus use the sign of equality in the above sense. The application of the axiom of reducibility to identity is explained in more detail for a few pages from page 59 onwards of the introduction." And I'll just try to clarify some of the comments made on page 180, immediately preceding the statements and demonstration of proposition 13.3. These comments are relating primarily to the application of proposition 10.221 in the demonstration of proposition 13.3. It appears that in lines 4 and 5 of the demonstration that we have the common components phi a and x equals a. However, we can't be sure that the x equals a which appears in line 4 is the same as the x equals a which appears in line 5, whereas we can be sure that the phi a is the same in both lines 4 and 5. Whitehead and Russell say that x equals a is typically ambiguous, meaning that the identity symbol may mean different things due to systematic ambiguity, depending on the specific types of x and a. However, phi blank is a fixed function, and its variable can only range over a single fixed type. Therefore, the variable of phi must be the same in both lines 4 and 5. Therefore, we can identify the a in each of lines 4 and 5, and once we've done that, we can go on to identify the x in each of lines 4 and 5. However, in the absence of a suitable component with which we can apply proposition 10.221 and identify the a's, then we would not be able to identify the x's. For example, if we have the propositions x equals a implies chi x and x equals b implies phi x implies psi x, both of these propositions may be true, but we can't be sure that the x in each of these propositions is the same x. All we can say is that x and a are of the same type in the first proposition, and x and b are of the same type in the second. The use of the letters x, a and b does not imply that x, a and b are individuals, by the way, and the use of the symbols phi, psi and chi does not suggest that these are functions of individuals. However, if we have the propositions the logical product of phi a and x equals a, and psi x implies phi b implies x equals b, then since phi is a fixed function, the variable a in the first assertion can be identified with the B of the second assertion, since A and B must be of the same type. Then since the proposition x equals A can only be significant when x and A are of the same type, then x must be of the same type as A, and since A is of the same type as B, then x must be of the same type as B, and thus the x which appears in each of the propositions can be identified. In the application of proposition 10.221 to obtain line 7, things are a bit easier, and since both phi A and phi x appear as components, then we can identify the a's first and the x's second, or the x's first and the a's second. And it's also worth noting that just because two variables can be identified doesn't mean that they have to be identified, and variables represented using different letters in different assertions may still be identified if they are of the same type as in the examples that I gave above, where A and B could be identified by virtue of the fact that they are of the same type. Section 14, Descriptions, is for me one of the most difficult sections to understand. There's much relating to descriptions that I don't yet fully appreciate, especially from the philosophical perspective. Nevertheless, I'll try to articulate my understanding of the contents of section 14 to the best of my ability. But I will openly admit that what follows will in no way be a complete and comprehensive treatment of descriptions. The treatment of descriptions in Principia Mathematica is more of a formal treatment than a philosophical treatment, and so, for the more philosophical aspects, it will be necessary to look elsewhere. There's quite a lot of preliminary stuff to cover before we actually get to the propositions of this section. Without the basics, in my opinion, this section will just be meaningless symbols, and it will be difficult to appreciate, even on a basic level, the significance of what's happening. On page 31 of the introduction we see, by a description, we mean a phrase of the form the so-and-so, or some equivalent form. A description of the form the so-and-so will only have an application in the event of there being one so-and-so and no more. We also see on page 181, a description is a phrase of the form the term which, etc., or more explicitly, the term x which satisfies phi blank, where phi blank is some function satisfied by one and only one argument. And finally, in Principles of Mathematics, section 56, the fact that description is possible, that we are able, by the employment of concepts, to designate a thing which is not a concept, is due to a logical relation between some concepts and some terms, in virtue of which such concepts inherently and logically denote such terms. Descriptions can be contrasted with proper names. A proper name is a symbol which directly represents an object. See page 69 of the introduction. A description is an indirect way of referring to an object, and this indirectness brings with it certain problems that have to be overcome. Some examples of descriptions are the round square, the present king of France, the author of Waverley, the Athenian philosopher who drank the hemlock. As we see, in some of these descriptive phrases, there is a specific object that is referred to or denoted. In other cases, though, there is no object to which the descriptive phrase refers. In other words, no object is denoted. This is never the case with proper names. There is no question of the existence of the object that a proper name represents. Something which does not exist, used in a very informal and more or less vague sense, simply receives no proper name. However, when a descriptive phrase is being used, we may not know whether there is actually a single object that the descriptive phrase refers to. Whitehead and Russell write on page 69 of the introduction, whenever the grammatical subject of a proposition can be supposed not to exist without rendering the proposition meaningless, it is plain that the grammatical subject is not a proper name, i.e., not a name directly representing some object. Descriptions are what Whitehead and Russell call incomplete symbols, and we see on page 69, by an incomplete symbol, we mean a symbol which is not supposed to have any meaning in isolation, but is only defined in certain contexts. We define the use of an incomplete symbol, but the symbol by itself remains without meaning. It is this, according to Whitehead and Russell, that, quote, distinguishes such symbols from what we may call proper names. The symbol, the so-and-so, can be roughly interpreted as the x which satisfies the propositional function phi x, and I'll often refer to this symbol simply as the so-and-so, or something similar. This is not to be understood as a definition of this symbol, but merely a way of informally interpreting this symbol. The symbol itself is without meaning. its use is defined as shown. In the definiendum, psi of the so-and-so should really be written as psi of the so-and-so in curly braces, but the curly braces are usually omitted. This definition requires some explanation, so I'll spend some time explaining some of the features and implications of this definition. I will for the time being ignore the symbol in the square brackets in the definiendum. This is relating to the scope of the description, which I will explain separately. What this definition roughly says, using similar wordings to that on page 71, is that the x satisfying phi x satisfies psi x, is to mean there is an object B such that phi x is true when and only when x is B and psi b is true. Or more exactly, there is a B such that phi x is always equivalent to x is a B and psi b. In this definition, the symbol the so-and-so appears only in the definiendum. It does not appear in the definiens. Thus the descriptive phrase, or at least its use, is defined in terms of proper names. As we see on page 71, in this, the so-and-so has completely disappeared. Thus, the so-and-so is merely symbolic and does not directly represent an object. We must understand then that the so-and-so in psi of the so-and-so is not a true argument of the propositional function psi. And this will have certain implications, as we'll see later in this section. Whitehead and Russell's definition of psi of the so-and-so does not commit us to the assumption that the x satisfying phi x actually exists. However, the issue of the existence of the object that is purported to be represented by a descriptive symbol is one of the main issues that have to be overcome, since we can still form propositions which involve a description, even when we don't know, and possibly have no way of knowing, if the x satisfying phi x exists. And the fact that we can form significant propositions rather than simply meaningless strings of symbols using descriptions means that we have to be able to determine the truth values of these propositions. But how do we deal with Russell's famous example, the present King of France is bald? The present King of France is a description, but it denotes no object. The proposition, the present King of France is bald, demands a truth value, either true or false, since the law of excluded middle is a true proposition in the system of Principia Mathematica. Of course, we may naturally feel inclined to assert that the proposition, the present King of France is bald, is false. Indeed, this is the truth value that this proposition will have. But we need a systematic way of assigning truth values to propositions containing descriptions where no object is denoted by the description. And unfortunately, it's not simply a case of saying that all propositions containing such descriptions are false. There are examples of propositions containing descriptions which denote no object, and yet the propositions will be obviously true, and this will be covered in more detail when I come on to the idea of the scope of a description. However, we will find that the truth of many propositions containing descriptions will require, as a condition or hypothesis, that the so-and-so actually exists. That is, that there is actually an object which is the so-and-so, and the only so-and-so, which satisfies phi x. The existence of the x which satisfies phi x is embodied in the definition 14.02. Note that the word exists or existence will be used in different contexts to mean different things. Existence of the x satisfying phi x is a derivative form of existence which is defined in terms of existence of proper names. Of course, we need to convince ourselves that this definition does actually do what we want it to do. The definiance of this definition is an actual proposition. We need to make sure that the right-hand side will be true only in the case where there is exactly one value which satisfies the propositional function phi x, and will be false in all other cases. Suppose that there is no x which satisfies phi x, that is, phi x is always false. Then we have the proposition phi b is equivalent to b equals b, where the left-hand side must be false, since phi x is false for all x, and in particular phi b is false. But b equals b is true, and so the equivalence is false. Therefore, the formal equivalence is false, and there is no b satisfying the formal equivalence of phi x, and x equals b. Now suppose we have exactly one value of x, say a, which satisfies phi x. Then clearly phi a is equivalent to a equals a is true. But in the case where x is c, with c not equal to a, then phi c is equivalent to c equals a is true, since phi c is false, and c equals a is false. Therefore, the formal equivalence of phi x and x equals a is true, and thus there is a b for which the formal equivalence of phi x and x equals b is true, namely when b is a. Now assume exactly two values of x satisfying phi x, c and d, with c and d not equal. Then we have that phi c is equivalent to c equals c is true, but phi c is equivalent to c equals d is false. Similarly, we have phi d equivalent to d equals d is true, but phi d equivalent to d equals c is false. Moreover, for a value of x other than c or d, we have that both phi x is equivalent to x equals c and phi x equivalent to x equals d are true. Thus the formal equivalence is false, and there is no b satisfying the formal equivalence of phi x and x equals b. A similar argument could be given for more than two values, but I think the point has been made. The right-hand side of definition 14.02 is true only in the case when there is exactly one value of x which satisfies the propositional function phi x. So as we see from this argument, our definition seems to work in the way that we want it to, and we will accept this definition. The scope of the description is, according to page 181, the proposition which is to be treated as the psi of the so-and-so. The example given by Whitehead and Russell is the one shown on the screen. In this case, the proposition which is to be treated as psi of the so-and-so is there exists b such that phi x is formally equivalent to x equals b and psi b. Since the two dots following the there exists b, group 2, extend over the two dots immediately preceding the psi b, since these dots represent a logical product, group 3, but do not extend further than the two dots on the left-hand side of the implication symbol, group 1. In the second case, however, we have the whole of the expression as the psi of the so-and-so, since the three dots following the there exists b extend over the whole expression, and moreover, the logical product, two dots, extends over both of the single dots on each side of the implication symbol and over both of the single dots on each side of the equivalence symbol. By the way, in each of these cases, the apparent variable x, which is indicated as a subscript on the right-hand side of the equivalence symbol, extends over the proposition phi x is equivalent to x equals b in both cases, since in neither case would the single dot on the left-hand side of the equivalence symbol extend over the sometimes apparent variable, and the single dot on the right-hand side would not extend over the logical product. Therefore, in the first case, the scope of the description is smaller than in the second example, and so in the first example, we would write as shown, where the single dot following the apparent variable, group 2, extends up to the single dot on the left-hand side of the implication symbol, group 1. The description in this case is said to have a secondary occurrence in this proposition, since the scope of the description is only part of the proposition. In the second case, we would write as shown, where the two dots following the apparent variable extend over both of the single dots on either side of the implication symbol. In this case, since the scope of the description is the whole of the proposition, it's said to have a primary occurrence. We see on page 72 of the introduction, when psi of the so-and-so, as above defined, page 71, forms part of some other proposition, we shall say that the so-and-so has a secondary occurrence. When the so-and-so has a secondary occurrence, a proposition in which it occurs may be true, even when the so-and-so does not exist. The notation to indicate the scope is admittedly very cumbersome, and Whitehead and Russell seem to agree. Therefore, they introduce a couple of conventions regarding the scope, so that it doesn't need to be explicitly mentioned every time. Only in certain cases will the scope need to be clarified. One of the conventions is that whenever the scope is not explicitly mentioned, it will be assumed that the scope is the smallest proposition enclosed in dots or brackets in which the so-and-so occurs. The second convention is that in cases where there are two descriptions involved, for example, f of a description and another description, it will be assumed in the absence of explicit mention to the contrary that whichever description occurs first typographically will have the larger scope. Thus, the x which satisfies phi x will have the larger scope in f of the x which satisfies phi x and the x which satisfies psi x, since it occurs first typographically. This convention that the description which occurs typographically first has the largest scope unless otherwise indicated is a purely arbitrary convention and, in light of proposition 14.113, which shows that in a proposition in which there are two descriptions, it is irrelevant which has the largest scope. We see that if the convention had been that the description which occurs typographically first has the smaller scope, then it would make no substantial difference ultimately. There are some other minor details regarding scope that Whitehead and Russell go on further to discuss, but which I leave up to you to read for yourself. It will be immediately apparent to anyone working through the demonstrations of this section that the demonstrations are sometimes quite messy looking. We have to bear in mind that the symbol for the so-and-so, which satisfies phi x, is an abbreviation of the much more involved expression given in definition 14.01, and we have to be a bit careful initially about applying the results from sections 1 to 13 directly to propositions which involve the description symbol, because this symbol may behave in unexpected ways. Many of the propositions in this section are proved by, much of the time, simply eliminating any descriptions using definition 14.01 or proposition 14.1. Once the description has been eliminated, then results from previous sections can easily be applied to the resulting propositions. However, once we have established sufficiently many of the formal properties of descriptions, then it becomes possible to apply the results of sections 1 to 13 directly to propositions involving descriptions. This will obviously result in much simplification in the demonstrations, but we have to figure out the formal properties of descriptions via the equivalent expression of 14.1 initially. The default or safe option, if in any doubt, is to replace the description with the expression that it is an abbreviation for. There's a gradual shift towards applying the results of sections 1 to 13 directly to propositions involving descriptions as the formal properties become clearer, and also through necessity to keep the demonstrations to a reasonable length and to avoid overly pedantic repetition. In the introduction on page 86, we see a list of 5 propositions from this section: 14.18, 14.16, 14.28, 14.131 and 14.144, and through these propositions Whitehead and Russell say that the use of the symbol the so-and-so, as if in f of the so-and-so it directly represented an argument to the function f blank, is rendered possible. We must be aware throughout that the symbol the so-and-so is not a true argument in a propositional function, and thus psi of the so-and-so is not a value of the propositional function psi. As we'll see, because of this, there are some propositions which would at first glance appear to be trivial consequences of propositions already proved, but alas, this is not the case, and this will be seen once the description symbol has been replaced with its equivalent expression using, say, 14.1. Since psi of the so-and-so is not a true value of the propositional function psi, then it may be that psi x always is true, but psi of the so-and-so is false. This will of course occur when the so-and-so does not exist. See proposition 14.18, which requires the existence of the so-and-so as a condition. Interestingly, identity in relation to symbols of the form the so-and-so is unconditionally symmetric. See proposition 14.131, and unconditionally transitive. See propositions 14.14, 14.142 and 144 and so on. But the reflexive property requires the condition of the existence of the so-and-so. In other words, if it is not the case that the so-and-so exists, then the proposition the so-and-so equals the so-and-so is false. As an example, the present King of France does not have identity with the present King of France by virtue of the fact that the present King of France does not exist. Note that to make sense of an identity involving descriptions, then we have to turn to definition 14.01. We can only understand an identity involving a description through this definition. Hence the comment on page 186 following the demonstration of proposition 14.13, which says that this proposition is not an immediate consequence of proposition 13.16, symmetry of the relation of identity, since a equals the so-and-so is not a value of the propositional function x equals y. Since a proposition such as a equals the so-and-so is not a value of the propositional function x equals y, then we come to one of the most important uses of descriptions, which is to assert identity in a non-trivial way. We see on page 24, it may be thought that identity would not have much importance, since it can only hold between x and y if x and y are different symbols for the same object. This view, however, does not apply to what we should call descriptive phrases, i.e. the so-and-so. It is in regard to such phrases that identity is important. And in Principles of Mathematics we see in section 64, when a term is given, the assertion of its identity with itself, though true, is perfectly futile. But where denoting concepts are introduced, identity is at once seen to be significant. In this case, of course, there is involved, though not asserted, a relation of the denoting concepts to the term, or of two denoting concepts to each other. That descriptions can be used to assert identity in a non-trivial way is demonstrated in propositions 14.13 and 14.131. In proposition 14.13, we have a proper name and a description. In proposition 14.131, we have two descriptions. And more concrete examples of non-trivial assertions of identity are, to use some of Russell's examples, Scott is the author of Waverley, which contains a proper name, Scott, and a description, the author of Waverley. Another example from the Principles of Mathematics is, the present Pope is the last survivor of his generation, which contains two descriptions, the present Pope and the last survivor of his generation. On page 70 we see the passage, a equals the so-and-so is not a value of the propositional function a equals y, from which it follows that the so-and-so is not a value of y. But since y may be anything, it follows that the so-and-so is nothing. The demonstration of 14.14 is omitted since it's seemingly a direct application of 13.13, where we have psi b is b equals the so-and-so, and therefore the argument of psi is being replaced by a different symbol, a, which represents a proper name and not a description. Thus the argument of psi is arguably not being substituted with any expression representing a description. Of course, if we're in any doubt, then we could use definition 14.01 or proposition 14.1 if we wanted to, as shown. What we see in many of the propositions of this section is that whenever a description is identical to a certain object, then the symbol which directly refers to the object can be replaced with the description without affecting things. For example, see propositions 14.17 and 14.171. The propositions 14.31 to 14.34 show how the scope of a description may be manipulated. Many of these propositions require as a condition that the so-and-so exists. However, 14.34 does not require this condition. Proposition 14.204 says that when the so-and-so exists, then there is a certain object which is denoted by the so-and-so. And whenever the so-and-so exists, then it has all of the logical properties of the object which it denotes. And this is expressed in proposition 14.18. I found that getting comfortable with dot notation was a big help in better understanding the demonstrations of the various propositions in this section. The demonstrations are often not difficult, but can be a bit confusing at first if you haven't quite got your head around dot notation. But I find this chapter fascinating. It would be quite easy for me to get carried away and just go through each and every proposition of this chapter, because nearly all of them seem to have some significance in and of themselves. However, I think I've mentioned enough for now. If you'd like to know more about descriptions, then there is quite an extensive range of literature relating to various aspects of descriptions from the last century or so. I haven't read even a fraction of what's available, so what I've mentioned in this video doesn't even scratch the surface. I'd recommend anyone interested to peruse the literature at his leisure to get a better idea of what the significance of descriptions is. And that brings us to the end of this video and to the end of section B of part 1. The next video will take a look at section C, which covers some theory on classes and relations. Please let me know if there's anything that you need further explanation for, either in this video or any other video on my channel. Please remember to subscribe and share this video with anyone that you think may find it interesting or useful. Thanks for watching.